Welcome to my virtual class. This is the 10th of April 2020. My name is Omeri. Welcome to the physics class of Unit 3.2 of the topic electromagnetic spectrum. Our learning outcomes will be description of how light is part of a continuous electromagnetic spectrum. Description of the order of electromagnetic spectrum in terms of decreasing wavelength and increasing frequency. Explaining some uses of EM radiations. And explaining detrimental effects of excessive exposure of the human body to electromagnetic waves. And the description of simple protective measures against the risks. Now, the electromagnetic spectrum is produced by the interaction of magnetic and electric fields. Now, when this spectrum is produced, spectrum means that there's a range of at least 7, and in this case we have gamma, X-ray, ultraviolet, infrared, microwave, and radio waves. But the visible light, which we can be able to see, it is just here, and it's also a spectrum of violet, blue, green, yellow, orange, and red. Very important. Now look at red. Red has a longer wavelength and a shorter frequency, and the low frequency. Violet has a shorter wavelength and a higher frequency. Very important to note that in this place here. Now what is important here is to look at the properties of waves in this unit. The first property of waves they all transfer energy. All EM waves are transverse waves. All EM waves travel at the speed of 300 millimeters per second at the speed of light in free space. All of them can be reflected or be refracted. Very, very important. Question. State the wave equation. State the wave equation. Do you still remember the wave equation? Do you still remember the wave? If they ask us to state the wave equation, we know that the wave equation we say is that speed is equal to frequency times wavelength, f lambda. Very important. We have been able to scale up what is important here in electromagnetic spectrum, and we've said that EM waves are produced when electric fields and magnetic fields interact with each other. That is very, very important. As we proceed on to learn this, most importantly, the properties of waves, as we've ever seen, that all these waves be able to transfer energy among other properties like refraction, and polarization. Now look at this question. Yellow light has a wavelength of 5.7 times 10⁻⁷ meters. What is the frequency and period of yellow light waves? They've given us wavelength and the frequency and period. Attempt it and send this answer to my stream, and if you are not able to do that, if you're not able to post your work on the Google Classroom app, send a short text message to 07488 21715. Let's try to attempt this question. They've told us that the wavelength here lambda is equal to 5.7 times 10 raised to negative 7 meters. And since we know that speed is equal to frequency lambda, then we could be able to say that speed, which is 300 million, is equal to f times 5.7 times 10 raised to negative 7. And therefore our f is going to be 3.0 times 10 raised to 8 divided by 5.7 times 10 raised to negative 7, which gives us 3.0 times 10 over 5.7. That is the resultant. This is our f, and since you get f, you can say t is equal to 1 over f, which is equivalent to 5.7 over 30. So that is our t in seconds. So that's how to solve this work here in a very easy way. I think that is very important. What is important is that we'll be looking at the properties of each of the waves in the spectrum, and we shall start with the radio waves. The radio waves, they have typical frequency of 10.5 to 10.10 Hz, and they have a typical wavelength of 10.3 to 10⁻³ meters. And the source of the wave is radio transmitters. Source of radio waves is radio transmitters. Very important. And also TV transmitters. The radio wave detectors include the radio aerial and the TV aerial. Very important. And the uses of radio waves. 1. Radio waves are used for transmission of sound and television signals. Also, radio waves are used for transmission of data in coded form. Also, they're used in radar, that's radio detection and ranging, where it is used for sending out signals and picking up their reflections from objects in their path. There are also the long-range radio signals enable astronauts to communicate with the Earth from the Moon and carry information from space probes as they travel to distant planets. Also, they're used in the navigation of ships and aircrafts. They're also used for satellite navigation. Radio signals sent from GPS are used for precise indication of position by spatial receivers. Very important. Next time we'll be looking at the microwaves in our second part of Unit 3.2. My name is Omeri. You have a video to watch here on the formation of EM waves.
Humans are completely surrounded by electromagnetic radiation. Have you ever thought of the physics behind these traveling electromagnetic waves? The great scientist Heinrich Hertz was the first man to transmit and detect electromagnetic waves. In his famous experiment, a high-voltage current was applied to the two ends of two metal wires, which generated a spark in the gap between them. This spark resulted in the radiation of electromagnetic waves. Those electromagnetic waves traveled through the air and created a spark in a metal coil located over a meter away. If you had placed an LED in that gap, the bulb would have glowed. This was a clear case of electromagnetic wave propagation and detection. However, before Hertz, the brilliant mathematician James Clerk Maxwell had already laid out the foundations for electromagnetic radiation by formulating 4 mathematical equations. However, these equations and the Hertz experiment raised a question: how do electromagnetic fields detach themselves from wires and propagate through a space? More specifically, what we need is a traveling electromagnetic wave and not a fluctuating one. Let's explore this logically. Consider an electric charge, which is moving at a constant speed. The electric field around it is shown. Now, imagine for a fraction of a second it accelerates. After that, it continues its uniform motion at a higher speed. What we need to understand is the effect of this acceleration on the electric field. The interesting thing is that the information does not travel at an infinite speed. Instead, it travels at the speed of light. Similarly, the information about the sudden variation of velocity of the charge does not get conveyed to the whole electric field region. The field near it knows about it, but the field far away still has no idea that the charge has accelerated and it is still in the old state. Let's separate out these regions with the help of two circles. Since the electric field cannot break, the field between these distances must transition. This transition field is known as a kink. The kink moves or radiates outwards at the speed of light. To show the kink animation in a clear way, let's move the camera along with the charge. We can say here that the acceleration of the charge has caused an electromagnetic disturbance or electromagnetic radiation. Based on this understanding, we will be able to understand the most important experiment in the field of antenna technology, the oscillating electric dipole. The interesting fact about this simple oscillating dipole is that it produces electromagnetic radiation in a perfectly sinusoidal manner. Let's see how it is achieved. Before getting into the electromagnetics, let's understand how velocity and acceleration vary in this simple case. It is clear that at both ends the velocities should be zero, and in the middle the velocity should be at the maximum. This means that this is a case of continuous acceleration and deceleration. The electric field pattern is drawn here when the chargers are far apart and when the velocity is zero. In order to have a better understanding, let's examine one of the electric field lines. Let's observe the electric field line at t by 8. You can see that the electric field line is deformed. The reason for this deformation is simple. This time period is the region with the highest acceleration. As we saw earlier, accelerating or decelerating charges cause kinks in the electric field. In short, the old electric field does not get adjusted to the new field very well. This deformation is continuous since there is continuous acceleration in the charge. When two charges meet at the central point, the deformed line also meets there. After that it detaches and radiates. This radiation travels at the speed of light. If you plot an electric field intensity variation with respect to length, you can see that the radiation we have produced is perfectly sinusoidal in nature. Please note that this varying electric field will automatically generate a varying magnetic field perpendicular to it. Now let's have a look at how this applies to an antenna. A time-varying voltage is applied to the metal wire as shown. Due to the effect of the voltage, the electrons will be displaced from right to left and create positive and negative charges. With a continuous variation of voltage, the positive and negative charges will shuttle back and forth in the wire. This simple arrangement is known as a dipole antenna. The dipole antenna produces the same radiation as we saw in the previous section. In this case, the antenna works as a transmitter. The frequency of the transmitted signal will be the same as the frequency of the applied voltage signal. The same antenna can act as a receiver if the operation of the antenna is reversed. When propagating electromagnetic waves strike the antenna, the oscillating fields of waves create positive and negative charges at the ends of the antenna. The varying charge accumulation means a varying voltage signal is produced at the center of the antenna. This voltage signal is the output when the antenna works as a receiver. We can note here that for perfect transmission or reception, the length of the antenna should be half of the wavelength. This is the first antenna design criterion for proper reception or transmission. The second most important design criterion is a term called impedance matching. Perfect impedance matching will make sure that the waves are radiated in the most efficient way.
Thank you very much. That was our lesson today. My name is Omeri. Goodbye.